other things, he studied Markov processes. What are Markov processes? A Markov process is a chain of events that is memoryless. That is, it is the assumption that the next event that will happen depends only on what is happening now and not what happened previously. A simple example of a Markov process might be a person. We'll call her Romy. Let's say that Romy can travel between 3 different possible places: work, home, and the Eiffel Tower. In this Markov model, each of these 3 locations is called a state. Now what we need is a series of transition probabilities. Transition probabilities tell us which state Romy is likely to travel to, given where she is. Let's assign a set of transition probabilities to each of the states. Every time Romy travels, we call that a transition event. In this model, if Romy is at home, she has a 0.5 chance of going to work, a 0.4 chance of staying at home, and a 0.1 chance of going to the Eiffel Tower. Notice that all of these transition probabilities sum together equal 1. All transition probabilities going out of a state should always sum to 1. How do we choose these numbers? Well, typically, we have to watch a process and count how many times a transition takes place. In our case, we have to watch Romy as she moves around. Let's say that we see Romy leave home 10 times, and she goes to work 5 out of those 10 times. This gives us a probability of 0.5 that if Romy is at home, she will go to work next. Once we have all these statistics, we can construct our Markov model. Typically, our transition probabilities are entered into a transition matrix. Notice that each of the columns of the matrix represents the state Romy came from, and each of the rows represents the state she is going to. Using this matrix, we can compute all sorts of useful quantities. So how do we use it? Well, first, we need a starting probability vector that represents what we know about Romy's starting location. Let's say we know with probability 1 that she starts at home. If we multiply our transition matrix by this starting probability vector, then we get a new vector representing our prediction about where Romy will be 1 event in the future. We can apply the transition matrix again to see where Romy will be 2 events in the future. If we keep multiplying these transition matrices, then we can make a prediction where Romy will be at any time in the future, even if that time approaches infinity. Markov models can be a useful and powerful tool. Take it from Romy. Markov models are great.
All right, guys. This is just an example of the Markov chain as we've been looking at it from yesterday's session. So the Markov chain is just one of the methods or mathematical method that is used in probabilities in order for us to calculate the probability or the outcome, which is used in machine learning and many prediction that you're going to have. So many of the AI tools that you see on the market have been trained using Markov series. So basically, most of the other probability methods will look at what has happened previously to predict what is happening tomorrow. But with Markov will focus on the current state, what's happening now. So it basically, let's say, for example, you want to look at the weather to predict what will happen tomorrow. So if you look at the weather from other probability system will look at what happened yesterday and to try and predict tomorrow. But Markov will look at what's happening now, today, to try and predict what will happen tomorrow. So when we're looking at the Markov chain, so the Markov chain is just a stochastic process. So basically, it's just a mathematical model that is used to describe a system that transitions from one state to another state So where each new state depends only on the current state. So not on the full history of what happened previously. So this is known as the Markov property. So that's how Markov will work. So each step of Markov chain, so the system can transition from one state to another or remain in the current state. That's how we got the example there that you've seen that video where it either the person goes to the tower or they go to another direction or they stay home. So in this case now, based on the probability distribution, the state change is called the transition. So we can transit. Let's say here it's a rainy day. So what's the probability of the weather changing from a rainy to a sunny, or changing from a rainy to a cloudy, or remaining a rainy day? So in this case, for example, in this example, we have the probability of the weather changing from rainy to sunny is 0.1, from rainy to cloudy is 0.3. That total will give us 0.4. And then the probability of the weather not changing is 0.6. So in total, we have 1. So total is 1, which is 100%. Okay. So, and the probability associated with different state changes is called the transition probability. So these are the transition probability. So these are the transition probability. So now this is how the Markov chain will work. So basically understand that the Markov chain is a sequence of events, right? Where the probability of each next state depend only, remember that it depend only on the current, on the present state, and not on how you got there. You understand? So there's no memory. There's no another example. When we're looking at this example that I give you now is this is the weather state that we have. So if today is sunny, tomorrow it might be maybe 70% chance of it to be sunny, 20% chance cloudy, 10% rainy. So when you look at something like that, so the future weather depends only on today's weather, not last week weather or anything like that. So that's how Markov will work. So in a Markov, that's where we're going to have a transition matrix. A transition matrix is when we will represent all these transition. The transition, it means from sunny to cloudy, what's the percentage there? So we take all those probabilities, we create a transition matrix, and the transition matrix is going to, that's where all the calculation is going to be done. So when you look at the Markov chain, it's used to generate, for example, text in natural language processing and machine learning. So example, you want to say, I am a student. So the next words depend only on the current word. So if I start by saying I, so the next word is am. So it's predicting the next word only. It doesn't matter where you were coming from, what was the story about. So that's how Markov is used. So Markov is used in things such as chatbots, autocomplete. So when you think, okay, the simple example is this. Look at your phone, your WhatsApp, when you're trying to type a message. As you start to type a certain alphabet, it can predict the rest of the sentence. It doesn't matter what you were writing in a message. So if you want to write, it's only focus on what you are doing now. It doesn't matter how long was your message. So it's focus on the words you are trying to write now. So that is Markov chain that is working on your what you call that, on your WhatsApp. All right. So we have so in Markov we will have the principle. Remember what we say: the state will depend on the current state, not on the past. So certain properties that we're going to have is the positivity, which means that each element in a state transition matrix is referred as a state transition probability. according to the probability theory. So this is expressed as the probability that we have, and the sum of those probabilities needs to be 1. So if we look at we have, how many options do we have? If we have 3 options, all those probabilities from state transition probability, all those probabilities, that means that moving from one state to another state, so that is the state transition probability. So moving from one probability to another probability. So when in the Markov process, so when we had all those probabilities, we need to get 1. So if a system, let's say a system of a state I at a certain time t, the state transition probability in that case will just be the state for that moment. So that will represent the probability that the system will move from one state to the next state at a given time. So you need to understand that that change will depend only on the current state. So it doesn't depend on early state. So that is the Markov property. All right. So now when we're looking at that, we can a certain Markov model. It's an example of a Markov model. So for a problem, we have the initial distribution pi and the transition probability A. And at any given time t, we have the state OT. So this is the state that we have. So in our example, we have maybe the state, which is maybe it's a rainy day today. This is the time. So the time is today, so it's raining. And then we have the state transition over time to another state, generating an observable sequence, which is state sequence. So the state sequence will depend. So you have maybe in our case, we only have 3 state sequence. So we're gonna have a rainy, sunny, and cloudy, right? But here we have many sequences. So these are the sequence at each time. At time 1, this is what we will observe. At time 2, this is what we're gonna have. So so the probability of such a sequence, so this is the probability, right? So the probability of that. So so in a Markov chain learning problem, so we have the initial probability, and then we have the transition probability, and then we have the states, which will be the states for each option that we have there in our sequence. You understand? So in our sequence, we're going to have many type of states. So you need to note that the Markov model itself will describe a system that transition between states, with certain probabilities. The key property of that is the Markov property, which means that the next state depend only on the current state, not on the past state. And then we have some prediction problem, which means that when we're looking at the prediction problem, we're looking at the main goal. The main goal is to calculate the probability of an observed sequence of states. All right. So when we look at that, the input in that case will be the initial probability, right? So the input will be the initial probability. So the initial probability, or usually represented by pi, the initial probability is the probability of starting each state, right? And then we have the transition probability. The transition probability is a probability is usually represented by P, maybe moving from A to A. That means we're remaining in the same state, or from A to B, from A to C, from B to A. So those are the probability, the transition probability. So this transition probability are actually the probability of moving from states, like in this case, from state A to state B. You understand that? And then we're going to have the state S, which means all possible states. So these are all the possible states that we're going to have. So an example here, we have, for example, state A, state B, state C. So the sequence will be maybe moving from A to A. That means we're not changing, or moving from A to B, right? In this case, A to A, that means we're not changing, or here we're moving from A to B, that's the sequence, or from A to C or B to C, you understand, B to A, that's the thing. So then we're going to compute the sequence using pi, which is the initial probability and the transition probability. So so now when we're looking at the Markov chain prediction algorithm, which is what we're going to observe here, A to B, A to C, you know, these are the just observation that we have there. Okay. Okay, so looking at the Markov chain probability here. So this is how it's represented. So basically, this is just showing you that these are the sequence that we're having, right? And this is how the sequences are going to move. So given the Markov model with known initial probability pi, and then we have also the transition probability here, and the state S. This is the all possible states that we can have. So we need to calculate the probability of the following sequence occurring. So when you look at this, if I can give you an explanation on this. So basically here, we're going to start with the initial probability for the first state, which is A. So the first probability here, probability of A. And then we multiply by the transition probabilities for each step. So we start with A. Remember, these are this all sequence that we have. We have AB, AA, BC, CB, CA, and so on. So we're now going to start with the probability of A. So what's the probability of this, which is the initial probability? And then we multiply by the probability of moving from A to A. So what's the probability? Let's say that probability was 0.2, which is 20%. So we multiply by that. So here we're going to start with pi, which is the initial probability. So pi times 0.2 times the probability of moving from B to A, you understand, times the probability of moving from C to B. You understand? So now we take this, we multiply the transition probabilities for each step. So this works because of the Markov property. So only previous state matters. All right. So the key insight of this is that the probability calculation is straightforward because all required probabilities are known. All right. So so according to Markov property, the probability of state at time n-1 is only dependent on the state n. So the probability of the tomorrow is depending on what's happening today. The probability of the next step will depend on what's happening now. So we don't care about what has happened before. So this is used most like in robotics. When you're creating robots, it doesn't matter what happened before. So if your robot has to go from one room to another room, so what matters is each step. It doesn't matter how many steps it did right in the past. So the next step is more important. So the next step depends on what step it takes now. So that's how it works. So you have the Markov, what you call this. So when we talk about the when we talk about the Markov chain exhaustive method, when we talk about exhaustive method, in this case, when we have the exhaustive method, it means that when we're learning the Markov model, we use exhaustive methods, also known as probability approximation. So the more sample sequence data we obtain, the higher the accuracy of the parameter. So in this case here, in this method, we don't know this pi, which is the initial probability. So we don't know pi and the transition probability beforehand. And then we estimate them from observed sequences. So the exhaustive probability will basically, in this case, we're going to take maybe the numbers of sequence starting with states, with a certain state, divided by the total sequences, right? And then we can calculate as well the transition probability, which will be the numbers of transition from a certain point to another point, divided by the total transition. All right, so in this example, for example, in this example where suppose we have data like red, blue, red. Okay, using the exhausting method, we can obtain the initial probability, because remember, in this case, in the exhaustive method is when we don't know the initial probability. So we can obtain the initial probability and the transition probabilities by estimating them based on what we've observed. So the initial probability, we're going to take the numbers of sequence starting from the first one, which is this one. All right, we divide by the total sequences. So we have 1, 2, 3, 4. All right, so in this case, when we look at this data here, so we're going to have 0.75 for red and 0.25 for blue. All right, so this is how we're going to have that. Okay, so when we count all these data, so we have 0.75 for red and 0.25 for blue. All right, and then the transition probability can also be calculated by counting the transitions. So that's how we're going to have that. The probability go from red to blue is 1/3, and then yeah, we can move from there. All right, so we have these Markov chain. When we look at the Markov chain learning problems, all right. So the Markov chains will actually, why do we need to do that? Because in real world problems, parameters can be unknown. So we learn from observed data sequences. So what we need to learn from that is the initial probability, the transition metrics, you understand? So, and then we can actually have all the information that we need to have to do the Markov chain. So now, which means that it takes us back to an algorithm that is used in what you call this, in speech processing, when we have to convert text to speech or speech to text. Those algorithms, you have the algorithm that we spoke about yesterday, which is the HMM. The HMM is the Eden Markov model. So this algorithm here, which can look at certain data. So let's say in this case now, we have this data that are looking at the moods, which can influence the activity. So the moods can influence if you want to play soccer, you want to listen to music, or you want to watch a movie. So those are the states that are going to happen. So let's assume J states are as follows. So as shown in the left diagram here, so J's moods every day is in one of the three states. Is either happy, unhappy, or neutral, right? So J is someone's name, obviously. So as shown in the right diagram, J's daily recreation activity are one, playing soccer. So depending on the mood, the action is going to take is playing soccer. listening to music, or watching TV. So these activities are influenced by the mood of the day. And the probability of choosing one of these activities will depend on the mood, right? So for example, when he is happy, the probability of watching TV is high. When he is unhappy, the probability of playing football is higher. So Jay's mood changes follow certain patterns, right? And his mood on the next day is influenced only by his mood on the previous day. So we don't care about any other day. All right. So in this case now, what we have is that the states we observe the output that will depend on hidden state, right? So we have hidden states which are the mood. Is he happy, unhappy, or neutral? And then we have observable states, which are the activities that is going to take. So the activity that is going to take, so the state that we're going to observe here, depend on the hidden states, which are the mood. So now these hidden states are the mood, happy, unhappy, neutral. And then the observable states are the activity, which are the football, music, and TV. All right, so the mood influences the activity, right? So the mood will influence the activity, but we only see the activity. So we don't know the mood, we only see the activity, but they were influenced by the mood. That's why these are called hidden states. So this is why in this case, the algorithm used is the HMM. Why? Because it's an hidden Markov model. So in the hidden Markov model, we're not just going to have normal state, observable states, but we're also going to have hidden states. All right, you understand? That's the difference with other algorithm, because in this case, we're going to have two different category of states. So we're going to have basically 5 elements in this case, where we're going to have what you call that. We're going to have the hidden states sets, right? We're going to have observable state sets. We're going to have initial probability, transitional probability, and what we will call emission probability. So in the current situation, J's mood sequence and recreation activity over some times are represented in the diagram below. So that's what we'll have. So we have the hidden sequence and the observable sequence. So we have that mood, happy, play football. We have those are the sequence that we're going to have in this case. So the states that cannot be directly observed are the hidden states, which is in this case the mood. And then the state that can directly be observed are observable states, which are the activities that J is going to take. All right, so now that suppose we look at this problem. So now we're going to have this state. This is the sequence that is going to happen there. So there will be 2 states, hidden and observable state. All right. So now, because we know that the mood will influence the activity, so we're going to have those hidden states, which are the mood, and the observable states, which are the activity. So now this is going to give us a dual stochastic process, which means we're going to have hidden states that can evolve, and each will emit an observable state. So each hidden state will emit an observable state. You understand? So this is how the problem is going to be. So basically on this case, we're going to compute the probability of an observed sequence, right? We're going to learn and estimate the parameters of this, and then we can easily find the most likely hidden state sequence that can happen. So the hidden state sequence, and then we can calculate the probability. So the current hidden states determine the probability distribution of the current observable state, and then the distribution of the next time step hidden state is influenced only on the current hidden state. All right, so the hidden state will influence themselves, and then they will influence the activity. All right, so you understand that in HMM, the hidden Markov model is essentially an extension of the standard Markov model. In this case, the difference is just that we also have hidden states. We don't just have observable states. So we have hidden states and observable states, and the probability relationship between these states, between the observable state and the hidden state. So yeah, so similar to the three elements of the Markov model, the HMM is determined by 5 key elements. So we have the hidden states, S, right? We have the observable states, sets, which we represent by R. We have the initial probability, okay? And then we have the hidden state transition probability. So between the hidden state, there will be a transition probability. And then each hidden state will emit an observable state. So which means that each hidden state here, we have the emission probability B. So which each hidden state will emit one of the probability, right? So this is what we have. So this is how it's going to happen. So you need to understand that in a normal standard Markov model, we're going to have 3 elements, right? But in the HMM, we're going to have 5 elements. All right. So in the standard Markov, we're just going to have the initial probability. We're going to have the initial probability. We're going to have the states, which we represent as a state sets, yes, and then we're going to have the transition probability. But in this case, we have 5 key elements. All right, guys. So this will be all for today. Any question before? Any question before we call it a day? Any question before we call it a day? All right, if there's no question, that's fine. All right, guys, I will see you tomorrow at 5:30 for HCIP Cloud and 6:45 for HCIP AI. Thank you. Have a great evening.